Good morning. Hello, everyone. Today, I'll be presenting our work on a GRU-based approach for botnet detection using deep learning technique. So, the presenter is Professor Suchetha ji, Assistant Professor, Sahyadri College of Engineering and Math. So, these are the contents that are being included in the slides. So, first, let us give the introduction on the GRU-based approach. So, botnets represent one of the biggest threats to cybersecurity, especially within the rapidly growing Internet of Things environment. These botnets are networks of compromised IoT devices that attackers use for the distributed denial of service attack, data breaches, and other cyber crimes. Since many IoT devices have limited security, they become easy target for the attackers. So this makes it challenging to detect the malicious activity in real time. So current machine learning models like random forest, k-nearest neighbors struggle with the variability of the network traffic in the IoT environment. As a result, they often exhibit reduced detection accuracy. So while deep learning models such as the LSTM GRU have shown better performance, they come with a high computational demand, making them unsuitable for the real-time applications and the resource limited of IoT device. So our research focuses on developing a scalable and efficient water detection system using the gated recurrent unit model, that is a GRU model. So we enhance this model with a select K-based feature selection to improve the performance by focusing only on the most relevant features. The primary objective of our study is to improve the detection accuracy while reducing the false positives and ensuring the model's applicability for real-time detection in IoT networks. So let us move on to the literature review, where we have put some of the reviews, like extinguished feature selection was used on the UNFP NBW15 dataset, improving accuracy and efficiency by performing well mainly for binary classification tasks, whereas an integrated rule-based IDS showed a good accuracy and reduced false alarms using the real-time datasets, but it struggled with detecting the zero-day attacks because it relied on the existing attack signatures. Another approach, you can see that there is a recursive feature elimination, that is RFE with a random forest to narrow down the number of features in the NSW NP15 dataset. Although the model achieved high accuracy, it missed out on the complex patterns by only focusing on a few features. So the solution using the KNN also with the genetic algorithms and PC demonstrated 99.99 accuracy, but it was limited to handling the noisy data. And finally, a multi-layer detection framework focused on a behavior-based and a flow-based analysis achieved good performance, but required further improvements to handle more diverse botnet activities. Few more papers have been compared the different models that has not been included here, but it has been put up in the journal paper. So next is a problem statement. So a problem statement is mainly increasing the growth of the IoT networks has participated in uh, precipitated a sharp rise in the cyber threats. But again, the comprehensive datasets like NSP and VW dataset offers the valuable insights in network traffic and cyber threats, but leveraging this data effectively for pattern detection in IoT networks remains a challenge. So traditional methods may not suffice to accurately detect and mitigate the botnet threats in the IoT environment due to the complexity and dynamic features of the attack. Therefore, there is a need for the advanced machine learning and deep learning technique to enhance the accuracy and efficiency of the botnet detection. Therefore, to address this critical gap, there is a required need for sophisticated machine learning and which would boost the security, resilience, and reliability of the IoT networks. So the novelty of the proposed GRU model is we have used a select key-based feature selection method where by using a chi-square scoring, the model pinpoints crucial features, boosting the efficiency and accuracy in the botnet detection while minimizing the computational complexity. So, a model also works effectively in the diverse and complex scenarios of the IoT in the comparison to the traditional machine learning model. So the simple GRU architecture as compared to the more complex models like LSTM enables the model to work efficiently while retaining high classification accuracy, precision, and recall. So given the limitations of the traditional ML and deep learning models in handling the IoT variability and resource constraints, the GRU model based model offers a scalable, efficient, and accurate solution for botnet detection. So the main objective of the work is to create a GRU model, then implement select K-based with the chi-square scoring, then focus on increasing the detection accuracy and minimizing the false positives. And we use a comprehensive data set for comparing our model with a different architecture, different machine learning algorithms and deep learning algorithms. So the proposed methodology, so what we have used is the Unisp data set. As we know, it is selected for um, because the ML, the traditional ML models, such as random forest KNN, struggle with the variability in the network traffic, resulting in the lower detection accuracy. And LSTM based deep learning models perform better, but are computationally too intensive, making them unsuitable for the real time IoT application. So our proposed solution addresses these challenges using the GRU-based detection system. The GR compared to LSTM offers a simpler and a fast architecture the while retaining the ability to capture the long-term dependencies. Additionally, we apply select K best feature selection to reduce the dataset's dimensionality using the chi-square scoring, ensuring that the most relevant features are used for the training. So with this combination, our system aims to achieve high accuracy, low false positives, while being lightweight enough for the real-time deployment in the resource-constrained IoT environments. So we can go with the algorithm here. The algorithm one for preprocessing. So it is in the algorithm one mainly focuses on preparing the data set for training, covering the feature selection, data splitting, scaling, and label encoding. So these steps ensures the model receives a clean, relevant, and a well-structured data. So you can see the feature selection using select K best uses chi-square scoring to select the top K features most relevant to the target variable. So this reduces the data complexity and ensures only the most informative features are trained. Then divides the data into training, validation, and testing sets. So this split allows for accurate evaluation and avoids overfitting by maintaining a separate test set. For feature scaling, applies standard scaler to scale the features to a standard rate. So scaling is important in machine learning to ensure that all the features contribute equally to the model learning. And lastly, we convert the categorical labels into a numerical using one encoder, and this coding label here we are building a model the GRU is having 128, then the dropout rate is 0.58 and GRU layer captures multiple dependencies by dropout rate. So using the Adam optimizer and the canonical cross information, which is ideal for then train is out of the what side which using validation data to monitor the performance. And this allows our model to learn effectively while adjusting for the potential overfitting. Also, we evaluate the model performance on the test data set that matrices such as the test loss and accuracy, validating the model's ability to generalize it. And then finally, we say the train model for feature is enabling the detection system to deploy without training. So next, we will go to the results. So the detection focuses on mainly presenting and interpreting the performance of a GR model in comparison with the learning. So with the curve the overall strength and limitation of our actors. So we have used the GRU, the and when combined the other the GI has given the best score to the FN score of 9.1529 balance of the other GI. So we can say we provide an simple performance on Botnet. Primary focus on the GRU models. So here in this, the GRU model combined with the select K-based feature selection. So here is we have used a select K-based feature selection method where along based on the chi-square score, and we can see which are the best features that will be. So by using select K-based, we're able to option not only improve the model quality but also application of the. So our matrices, the different models of our processed model, so the highest robustness, accuracy of 10.3%, surpassing the one of the best machine learning algorithm that is the random forest model, accuracy with 82 to 85%, 22.5% to 84.25%, and the LSTM model accuracy of. So this is the matrix where the figures A and A to F. So you can see logistic regression B for the decision tree, then D for the forest, for the GRU. It's a confusion matrix for the models, including the machine learning. Each matrix shows the models true positives, true negatives, false positives, and false negatives, giving a visual overview of how accurately each model classifying the data. So the key observation of this confusion matrix is that uh, final one, that is the GRU model, stands out for its minimal false positive and false negatives, indicating its high accuracy and reliability in the botnet detection. So this is reflected in the model high F1 score with 97.61%, which demonstrates the model's performance. So in contrast to the ML models like one of the random forest and the decision tree displaying higher false positive and false negative, highlight the challenges that these models face with the variability of the IoT networks. So we can see the performance models with the ROC curve and the uh, ROC curve and the loss curve. Okay, so the ROC curves is the referred operating characteristic curve for the GRU model, visually represents the trade-off between the true positive rate and the false positive rate. So the high AUC value for the GRU model confirms its ability to effectively distinguish between the botnet and the normal traffic, indicating robust application performance. Whereas the loss graph track both training and the validation loss across the multiple epochs, allowing the monitor the model learning and generalization. A steady decrease in the validation loss over epoch indicates that the model is not overfitting, suggesting that it's learning from the data in a way that it generalized to unseen, generalizable to the unseen cases. So together, the ROC curve and the loss curve validate the GRU model's high accuracy, reliability, and generalizability in real-time IoT settings. This combination demonstrates the model's readiness for practical deployment, balancing both high classification accuracy and stable performance. So as we know, so we can know that with always its LSTM when compared to the GRU, giving the higher accuracy compared to LSTM GRU optimized with optimized design, better suited and efficient data, getting the higher speed performance. So with the dropout regularization, GRU model showed improved robustness marked by the gradual decline in the validation of the LSTM in resistance to overfitting. So this is the tabular representation where the comparison of cover model and the GRU model performance with the existing machine learning model which has been investigated in the study. So table 1 summarizes the matrices of accuracy or for the different, including the physical models and the deep learning model. Science is the model's ability to correctly classify the while minimizing the error. So this is with and demonstrating its superiority in correctly identifying the content related data. related activity. So with precision of 98.10 and recall with that is balanced accurately detecting the code, which is essential for reducing the false alerts in IoT networks. For the low error rate of the GRU models also further emphasizes its effectiveness and dependability in the botnet detection or the conclusion. The compiled GRU model overall robustness and suitability for the botnet detection in IoT environments, especially the high accuracy and low error rate are critical for maintaining the network security. uh, Integration with the select, and one of the conclusion is that the integration of the GIS and select rest has proven effective in dimensionality reduction while preserving the accuracy. The high compute, however, the compression demands of the GRU model may present a challenge for the real-time IoT application, which the processing time and future research further optimizations to make the model more suitable for the real-time applications in IoT environment. This is the references again put up here. You can also refer of the paper or the specified references are being done, which could not be included here. Thank you.